Thank you, Paul. It's a pleasure to be here tonight to talk to you about how Santos, and also the industry is going about the business of exploring for, finding and hopefully in the future developing shale gas deposits that Martin has just talked about. So I plan to give you an overview of how we as Santos and industry go about our business, hopefully to give you the confidence in our operations and especially as it relates to water, because here we're here today to talk about the water impacts. So just before I start, that's a photo of an actual drilling rig in the Cooper Basin. It's not drilling for shale at that time, that was drilling for tight gas up in South Australia in the Cooper Basin. So I've also got the same slide that Martin had. Funny how great minds think alike here. However, I'll just explain a little bit different things with it. So you hear a lot of people talking about conventional gas and unconventional gas, and I get a lot of people saying, I want some of your conventional stuff, but I don't want any of that bad unconventional stuff. I don't want any of that gas. The gas is all the same, whether it comes out of coal seams, whether it comes out of tight sandstones, whether it comes out of conventional sandstones, whether it comes out of shales. The gas is methane, mostly methane. It does have some uncontaminants, depending on what the setting is. The unconventional term refers to what rock it is in and what you've got to do to get that out. So as Martin was explaining, the gas that is trapped in these unconventional reservoirs, or tight gas reservoirs as well, is in such a tight setting that it will not flow out economically. The conventional gas, which has been predominantly produced to date in the world, comes out when you drill into it. The gas will free flow out of that well at a reasonable economic rate. When we drill into the shales or even into the tight gas sands in the Cooper Basin, we see that the gas will not flow out economically and sometimes will not flow out at all, simply because it is trapped in such tight rocks. In actual fact, the cement pavements or the sidewalks that we all walk down on here today, that's got what we call more permeability, more flow potential for water to go through that than the rocks that we're chasing for here. And that's why we need to do something to get that gas out. That process is hydraulic fracture stimulation, to where we create those fine cracks in the rock, open up that rock to enable the gas to flow more freely into the rocks. It's like converting a dirt outback track where you might get one car going on a day into a superhighway to where we can get many more cars, many more gas molecules coming out so that we can produce this economically and get the gas to the marketplace. So how do we go about drilling wells? So this is a stylised example of a drill well here. This is a vertical well. So drilling a gas well can take, sometimes can take 5 to 7 days, sometimes can take many weeks. We've just started drilling a well up in the far reaches of the Northern Territory at a place called Tanambarini in the MacArthur Basin. That's forecast to take us 10 weeks to drill there because of the depth, because of the geology, because of the rocks we're going through, etc. Also, depending on whether you're going vertical or you turn the well to horizontal where you're going to drill greater distances, that will take longer as well. But as the hole is drilled, we then put in multiple concentric rings of pipe, which are then cemented in place. That cement is pumped down the inside and back up around the outside, sealing that off from the formations that it's been through. And critically what we look for, you'll see on the diagram there, and I won't try and point to it from where I'm standing here, you'll see the aquifers. Knowing where those aquifers are is absolutely critical to our business, to understand where they are, to make sure that we look after them, make sure we protect them. We protect them by drilling through them quickly with safe fluids. We then cement them off to make sure that that aquifer will not be able to flow anywhere, and also that the hydrocarbons far down below are then sealed off from it as well. So as I said, the cement is pumped down the inside of the pipe, back up the outside, and then forms a seal around there. It gives the well both mechanical integrity, but importantly from a water sense and from a hydrocarbon sense, it locks all those fluids in place back where they have been locked there for geologic time. Now, once you've drilled a well, the absolute critical thing for our business is well integrity. We've got to design the well correctly, we've got to use the right materials, we've then got to build it correctly, and then more importantly, we also have to maintain it correctly so that it can make sure it does the job that we're after, which is to get hydrocarbons out of the ground safely and efficiently forever and a day. And to not have any problems to where anything may leak into overlying water formations. So all of our wells at Santos, we have on a well integrity plan. This is based on risk assessment, where depending on what formations we've been through, what we're producing out of it, etc., we will then determine how often we need to visit those wells, what pressure testing regime we have to go through to make sure those wells are looked after for their lives. I'll cover about well decommissioning later on. I won't talk about it here. So we look at these things every year to make sure that all of our wells have the integrity required to carry on with. Now, if a leak does happen, and yes, it's an industrial process, a leak may happen, that will be on one of the inner strings of pipe. Now, we've got multiple layers of redundancy. We've got sometimes 3, 4, 5 layers of concentric steel pipes with cement, with another steel pipe outside it, with more cement outside, etc. There might be a leak in the inner one. We then pick that up through our routine surveillance methods, and we then solve that problem before it goes back out. It's got to go through 3 or 4 things before it actually can get out into an aquifer. Now on to fracture stimulation. So Martin sort of talked about an overview of it there before. So fracture stimulation, or fracking, is something that obviously probably you've heard a lot about. It's simply a process that enhances the productivity of the gas wells that we're after. Without it, we would not have a gas industry going in South Australia at the moment in the Cooper Basin. Now, it's also not a new process. You hear a lot of rhetoric in the press that we don't want, this is brand new process, it's not good. Well, the industry has been using it for over 60 years, and we in Australia have been using it for over 40 years. And in actual fact, in Australia, the industry has fracture stimulated over 2,000 wells in Australia, in Western Australia, in South Australia, in Queensland and the Northern Territory. The company I work for, Santos, we have done over 1,000 of those wells. We are the most experienced operating company in Australia using the technique of fracture stimulation. We have done all those wells, those 2,000 wells across Australia, the 1,000 wells for Santos, without any environmental harm. How do we know that? Our industry is very, very tightly regulated. We have the industry watchdogs looking over us all the time. They will come and see us. They see the outcomes of our operations. They come and check with us. Another point is that a lot of the fracture stimulation operations in Western Australia have been undertaken on Barrow Island. Now, Barrow Island is an A-class nature reserve. It's a very pristine environment where they've maintained that, but the oil wells that are drilled there, the majority of them have been fracture stimulated over the last 20 or 30 years. Again, without any detriment to the groundwater systems, that is still meant that is an A-class nature reserve. Now, as Martin talked about, the process of fracture stimulation involves pumping a fluid that is primarily water with sand, or actually proppant in the Cooper Basin. We would like to use sand, but we find that the sand actually, when it closes back on itself, will crush. So we actually use ceramic beads, a higher strength form of proppant material, to make sure it stays open. I've actually got some samples down here of both frac fluid and also of proppant. So at the end of the day, if you want to come up and have a look at those, please come and see it. So the fluid contains water, sand or proppant, and a small percentage of chemicals or additives. We pump that down under high pressure. As Martin said, that's to create those fine hair-like fractures in the rock to be able to open up, to be able to get the gas out. So as we pump it up, those cracks will open. Now, when we remove the fluid pressure, those cracks will then close again. That's the idea of the proppant. So we've got to transport this proppant material down into those cracks, so when it opens up, the proppant is packed in there, so then it can't close back on itself, and that way there's a highway left there for the gas to flow out of, so that we can then extract the hydrocarbons going on. Now, as I said, we at Santos have extensive experience of this. We've done over 1,000 wells mainly in the Cooper Basin, but also in the Northern Territory as well. And we're actually going to be doing 500 stimulation treatments this year in the Cooper Basin, all very heavily regulated by our regulator here in South Australia, DMITA. So chemicals, again, these get a lot of press. So why do we use them? We would prefer to use, and we do use, the least amount of chemicals possible. We are evaluating using what's called slick water treatments. Now, the term slick water, some people have misused that and they say that is very damaging. Slick water is actually virtually straight water. It's actually water with friction reducer to enable it to be pumped easier down a well. It hardly contains any chemicals. But we use chemicals to be able to augment, to be able to get the proppant in place. If you try and mix up sand in water and then try to pump it somewhere, you'll pump the water, but the sand gets left behind. So what we have to do to that fluid, we have to make it viscous. We have to have some carrying capacity. And that's what we do with what we call a viscosifying agent, or actually, it's actually bean flour. So if you ate ice cream last night, you actually ate bean flour, so you actually had a component of fracking fluid if you ate ice cream last night. We also use friction reducers. We're pumping a lot of fluid under high pressure. That takes a lot of hydraulic horsepower at surface. So what we do is we use friction reducers to be able to make that water, even though it is pretty slippery, we make it even more slipperier, so it reduces the amount of hydraulic horsepower we need to use at surface. Other things we do is we use biocides. This is because we're taking the water out of sources, it's open to the atmosphere, and that might contain microbes. That might, A, sour the reservoir, which we don't want to have happen. It also might break down the gelling agents we have, which will then mean that we can't use that fluid. So again, we use biocides. These are typically disinfectants. In actual fact, the disinfectants or the bleaching agents that probably a lot of people have in their homes and use to clean their house with, that is actually a stronger disinfectant than what we actually use in our fracturing operations. Other chemicals we use are scale and corrosion inhibitors. This is because we're pumping down those steel pipes. We want to make sure that the water that we're using there does not cause any scale or rust on those pipes. Another thing we also use is a chemical called a surface tension modifier. This is in effect a soap. When we pump that fluid down and place the proppant, we then want to get the majority of that fluid coming back. Now, because the grains are so tight, if you try and push water through there, and as Martin was describing, we're getting virtually down to the width of the water molecule. We have to make that water molecule easier to get out, so we put in place surface tension modifiers so that it doesn't cling to the side of the rock, it actually flows back out easy, so we can try and capture as much of that fluid coming back as possible. Now, another thing that I just want to highlight here is we don't use any BTEX chemicals. This is benzenes, toluenes, ethylbenzenes, xylenes in any of our fracture stimulant operations. We're also very open with what we pump. So we talk with openly in Queensland, in South Australia and Northern Territory. We are very strong on making sure that people know the ingredients of what we pump. Potentially not the recipe though. We'll tell you what's in it, but because some of these fluids are extremely engineered fluids, and this is like most other industrial products that have been developed. Coke will not tell you the formula of Coke, but they'll tell you what the ingredients are, but they won't tell you the recipe. We're the same. We'll tell you the ingredients, give you all the material safety data sheets, all the ecotoxicological reports, so you know what's there and what's going down the hole. What we won't tell you is exactly what is the exact formulation, because that's subject to intellectual property rights for the companies that we use that have developed those fluids. So on to water management. Water is a key component of the operations we do for drilling for gas and using in hydraulic fracture stimulation. We source that water from local boreholes, and we also use it from beneficial operations such as the produced water we get out of our oil operations in the Cooper Basin. If we have to use a bore water, we will work very closely with the stakeholders, particularly the pastoralists or the traditional owners, to find out where their bores are, if we can or can't use them, and if not, if we can't use them, we will then move away and drill another well. Typically, we will look to drill deeper than using potable water or water that is enough quality for cattle. We do not use, with the advent of new fluid chemistry, we can use brackish or saline water for our operations. We will seek to prefer to use those sources rather than using the critical potable or freshwater supplies. Now, as I said, we also reuse water from other operations, such as the produced formation water from adjacent oil and gas production in the Cooper. And that means today that we are actually drawing less bore water today, even though we are using more fracture stimulation treatments today than we used to do 5 or 10 years ago, because we've developed the fluid chemistry to where we are reusing water from other sources. So as I said, water is a key component. We'd use about 1 million litres when we drill a well, but we use 5 to 20 million litres when we fracture stimulate a well. It's not an exact science, so we can't tell you exactly how much we use on an average well, because each average well is different. On a vertical well, you might only do 2 or 3 fracture stimulation treatments. Therefore, you'll only use maybe 1 or 2 million litres. If you go to the big horizontal wells that Martin was talking about, that's where you might be doing 20, 30 stages or treatments in that, and that's where you might use the 20 million litres. Now, when we flow back that water, we capture it in line tanks and line pits, make sure that that does not get into the groundwater systems. We then dispose of that in an approved regulatory way. Now, the other thing we do to make sure we look after the environment, Martin was talking about fugitive emissions. When that fluid comes back out, it does have gas in it. What we do is we run it through a separator, we separate out the gas from the fluid, we then send the gas that is not able to be sent into the pipeline for sales gas. We actually flare that rather than vent it. Vent it is bad from a greenhouse perspective. Burning it reduces the greenhouse potential dramatically. Also, I'll just highlight that before we do any work in an area, and for instance, we've just started shale gas operations up in the MacArthur Basin up in the Northern Territory. The first thing we did before we did anything up there is we went up there and we took baseline surveys to understand what was the quality, what was the quantity of the groundwater in that area, so to make sure that we would not be disturbing it when we do operations going into the future. We've talked that through with the pastoralists and the traditional owners, and they're aware of operations, and we've then cited our bore for getting our water in conjunction with them. They actually wanted to put it closer than what we wanted to do because they want to use that water bore when we're finished with it. They want to use that for their stock operations as well. So, on to potential water impacts. As with any process, an industrial process, there are risks. But it's the same as when you walk across the street. There's a risk in doing that. I can't guarantee if you walk across the street, you won't get run over. The trick to it is to make sure, or the key to it is to make sure that you understand the risks and you put in place operational measures to make sure you minimise the chance of those happening and then minimise any outcomes if those risks do happen to take account of. So there are three key ways, and Martin sort of covered a couple of these, that hydraulic fracturing may lead to having water contamination. I guess the highest risk one is actually spills and leaks at surface. This is where we've just got trucks driving around at surface, delivering the fluids to the location, handling the chemicals at surface, etc. That is the largest risk we face. So what we do there is we handle all the chemicals in triple line bunded pits. We have very stringent procedures of how we do that. We also have lined pads so that they can't seep into the groundwater if there is a spill, etc. Another area where people have said that it may happen is where you get migration from when you're fracking way down below at say 2,500 metres. That will form a crack and will go up to at a depth of about 200 metres, but most typical household or stock water bores are. That simply cannot happen. There are many, many layers of impervious rock between us where we're fracking and up there, and also from the studies that we've undertaken in the Cooper Basin where we have mapped how high these fractures grow. They're only growing 150 to 200 metres. Martin had a document there that said it was up to 600 metres. All the evidence we've seen in a study that was done in the US of hundreds of thousands of fracks that was undertaken in the Barnett and the Woodford shales, the majority of those have only grown 200 metres. So it's vastly different to the hundreds to thousands of metres difference between where we're undertaking operations and where we're undertaking where the groundwater is. We will protect that groundwater. It is vital for us as well as also the people we live with. So a properly executed, the last one is if you get a complete failure of your well. That will only happen if you haven't done the right standards up front. We are closely regulated, so the regulator is there to ensure that people do not do the wrong thing. The other thing that may happen is if you drill in an area which is high tectonic or seismic activity, again, we site our wells taking that in mind so we don't drill anywhere near where any faults are. Because if you drill near a fault and that moves, that may cause an issue with your well. So if you build your well right, you look after it right, hydraulic fracturing does not pose any undue risk to the environment. Almost there. So on decommissioning. When a well is finished, its economic productive life, when we can no longer produce hydrocarbons out of it at an economic rate, there are still hydrocarbons in the wellbore. So what we do, we have to decommission that well according to very strict procedures. Exactly the same as drilling a well. You've got to make sure you do the right things to that well at the end of it. So what we do is we work closely with the regulators to find out or to determine where we place the isolation plugs. We use a specially engineered form of cement. This is not your household garden variety cement. This is much higher quality, much higher standard cement. We place those plugs to make sure that the hydrocarbons are kept where they are and also that the aquifers are kept where they are as well, so that the two can't come together. This cement will stay there because, in perpetuity, because there is no fluid flow down below, there is no air down below, so that cement will not break down. So if you look outside and see buildings, yes, you see the concrete falling off and stuff, etc. That's because that is open to fluid flow, air, water around you, etc., and is then degrading. Because we're in an anaerobic environment and because there is no fluid flow, if you abandon your well according to the best practices, it will not happen. So, just in closing, and thank you for your time, it's a pleasure to be here tonight. I hope I've given you some information that shows how the industry, and in particular how we as Santos do our business. We are a company that undertakes its operations in a way we are very proud of our record. We do strive to look after the environment and also to make sure we work in conjunction with all of our stakeholders. Now, some of the information I've given you here tonight may be at odds with what you may have heard from other sources. So, and yes, I hope you can trust me in saying that. What I've got here, though, is a couple of, reports that you can look up. And in particular, I'd encourage you to look up the ACOLA, which is the Australian Council of Learning Academies. These were the preeminent scientists from around 5 Australian academies that got together and undertook a study on shale gas and its benefits and its risks in the Australian context. They then developed a report and have published that you can download that. So if you just type ACOLA shale gas study into Google, you should come up with it. And I'd encourage you to go through and read that, and that's where they cover a lot of the benefits, a lot of the risks, etc., that both Martin and I have talked about tonight. There are another couple of things there. DMITA, our own state regulator, has also issued a report there as well you can get. And then APIA, our industry body, has also published a factual document that goes through the process, what I've talked about tonight. So, thank you.
Our final speaker this evening is Professor Craig Simmons, the Schultz Chair of the Environment at Flinders University and also Director of the National Centre for Groundwater Research and Training. Craig is a very highly respected research leader in Australia, and he is a member of the Statutory Independent Expert Scientific Committee on coal seam gas and large coal mining development. His expertise is in, the impact of these activities on the groundwater system. So thank you very much for coming along and presenting us today.